So if I have to state in one word, what is NP hardness assumption basically is, right? From where we could start the world. Okay. So what is the basic problem that we actually assume that cannot be solved in polynomial time? SAT. Okay. Okay. So here is a problem called 3 SAT or SAT. Okay. Now, so what is 3 SAT or SAT? So 3 SAT is basically input is a phi n variable formula over 0, 1. Okay. And say m clauses. Question is, does there exist a satisfying assignment? Okay. And you all know what is the meaning of this. Okay. So, so this is basically SAT. What is SAT? When you do not have any restrictions on, do not have any restriction on clause sizes. Okay. Now, what about 3 SAT? 3 SAT is the same problem, but clauses are of size at most 3. Is that fine? Okay. So, so the basic assumption of polytime algorithm basically is, polytime world is, what is a polytime world basic assumption? That look, SAT, 3 SAT cannot be solved in polytime unless every problem in NP can be solved in polytime. Right? So we do not know how to prove something cannot be done, right? But so we say that, look, we make the world, we make a world of problems, okay? We make a world of problems and say, look, all these problems fall together, okay? In the sense, their complexity or their computational, their algorithmic powers are limited with each other or related to each other, okay? So this is how we so witness that, look, how is it possible that so many different problems of different kind will show similar behavior? And that is what is the basic idea behind all this, like reductions and everything, okay? So this is what the polytime world is. A 3 SAT cannot be solved in polytime unless every problem in NP can be solved in polytime. Okay. So now I am going through all of you people one by one, and I'm asking you one problem each in world wherever you have seen it. Okay. Polytime, non-polytime. Okay. Okay. So can you just write, all of you write one problem in the chat box, any problem which you would have seen in algorithms or anywhere. Look, second time if you use, then you better come up with a different name. Okay. I did not ask for NP complete problems. I asked for okay. Okay. I don't have 16 problems, although there are some 13, 14 people in my class. Okay. Okay. Now let's try to understand. So you all have told up this definition of problems. Now I want to understand first. So the way we are going to show that, okay, if one of these problems here in this world can be solved in P time, imply others can also be solved in P time. Okay, so suppose there are two problems, A and B. Okay, so when I say that, look, if A can be solved in P time, implies B can also be solved in P time. What is the meaning of this? Like, what is the meaning of this? Anybody? When we say that a problem A can be solved in polytime, implies some problem B can also be solved in polytime. What is the meaning of this sentence?
Problem B is reducible to problem A.
I mean, that is a technical term, but like more common term should be what?
B is easier than A?
Yeah, yes, that's okay. But like, yes, all of you are equal, all of you are right. But there are much more simpler meaning of this. Like, this is, yeah, as difficult, and all these are like something which we hear. But what it actually means is not this. Actually, what it means basically is that, look, okay, whatever name you can give it to, what it actually means that, look, if you have an algorithm for A, here's an algorithm for A, here's an algorithm for A. It's an algorithm to solve A, right? If you have good algorithm, then I can make a good algorithm for B. What does it take? It takes an instance for B, converts it into an instance of A, and uses this answer and answer for I. You understand? This is basically the algorithm. This is what it means. That if you could design an algorithm for A, okay, then I can design, if you have a good algorithm for A, then I can design a good algorithm for B. Okay, this is all that it means in language. Okay, now the question is, now this is a box. So now, what is our main goal? Tell me, what is our main goal? We want to solve B in how much time?
Polytime.
Polytime. So, given an instance of B, I have to convert it into an instance of A. How much time should it take?
Polynomial time.
Okay. Okay. Right? It should take polynomial time. Otherwise, why it should take a polynomial time? If it takes something else, what's wrong in it?
Then we are using algorithm for A. Like if the reduction is taking more than polynomial time, then the overall time will be more than polynomial.
Yeah, excellent. Fine. Right? So it should take a polynomial time, and what it should do, it should output an instance of A. Right? So what is this phase? What is this phase? What is this called? Transforming a B to A. transforming problem B to A. Transforming problem B to problem A. What is this whole machinery? What is this called?
Polytime reduction.
This is reduction, and since it takes polynomial time, we call it polytime reduction. Okay. So first of all, this is exactly is reduction, right? And since it takes polytime, we call it p-time reduction. Okay. Now, this model of saying, oh, if I could do good algorithm for this, then I can design good algorithm for that. This can be said in any paradigm, any algorithmic model, and it exactly means the same thing. But what will change? The meaning of polynomial time will change, right? Because you need to answer something much more interesting and important. So for example, let's look at the setting which we are in, okay? I wanted to say some problem is like, say, pi1 is some problem. It has some input I and k, okay? And my parameter is k, okay? And question is something. Okay? And there is some question, okay? And next is another problem pi2. Input is I prime, k prime, parameter is k prime, and there is some question. I don't know what this question is, okay, something. And now I say, oh, let's say t. Let's say if we say, here is our statement, okay? If there exists an algorithm for pi1 running in time f of k time n to the time not n, what is the meaning of n? Let's say instance size to the power 1, then there exists an FPT algorithm for pi2. Okay, what is the corresponding box description for this? Right, we did this for polytime, right? So what will be the box description for this? Anybody? So what is given to you? You're given an algorithm for pi1, okay, which runs in some amount of time.
Then the outer box will be for pi2 and the inner box will be for pi1, and the reduction will be.
Wait. Let me draw. So this is a box for pi2, and there's an inner box for pi1. Am I right? Now, this guy takes instance I comma t, right? Now, what it should do? What it should do now?
Should transform the instance of pi2 to pi1.
Okay, so it should transform this instance of pi1, and based on answer, returns an answer for pi2. Am I right? Okay. So suppose this is I prime and some t prime. Okay, is that fine?
Yes.
Okay, now tell me question number 1. How much time does how much time should we allow to transform I comma t to I prime comma t prime? That's a question number one. What do you think? How much time should it be allowed to take?
So f of t n power constant.
Does anybody agree with
I
her?
power constant.
Yeah, but does anybody, apart from me, does anybody else agree with her? Because I don't seem to agree.
Yes.
With her. I don't agree with her. I think she's not telling the truth. Correct. Do you still agree with her? So C says, how much time should it take? How much time should we allow this? C said it should take how much? F. Am I right? F of t times. What is it? Is this F and this F same?
Oh, f of k. Sorry, it will be f of k, not f of t.
So the running time of pi1 is like f of the parameter, right? Times the instance to the power big of 1. This is what it takes pi1. Okay. Now, how much time should you take? Is this what she's saying is okay? Or she also changed her line. She also said this. Sani, am I right? Is this the two answers you have?
Yes.
Okay. I really want you to understand this, guys. Okay. This is whatever studies you will do. I mean, this will be this will hold you in a good faith if you are able to do these things. You don't have to remember many things in life. What is my ultimate goal? What is my ultimate goal? What is the ultimate goal for making this pi2? To design an algorithm, which is FPT in
T.
So suppose I'm shooting for an algorithm with running time, say h of t n to the power, or say some, h of t to the power, say some instance to the power big of 1. Okay. Suppose this is the kind of algorithm I'm shooting for. So should I constrain the running time where some h is some function? Like I'm shooting for this kind of algorithm for some function or any function. Like can we design such an algorithm for any function h? Okay. Okay. Now my question is, in the first real transformation, should I stop it to take time f of t, or can it be allowed something different, some different function? Hi guys, either you all are lost or you are not understanding.
It
If
can
not,
be
then
any function of
ask
of
question.
T.
Okay. So some person said, okay, so let it be allowed. Now this should depend on t or should depend on the k. Get this, okay? We are trying to design algorithm for pi2, okay? Now pi1 takes instance I comma k, and based on that it does something, okay? Now it should be h of t or h of k, what it is. Sonak?
I think it's h of t.
Okay. Anybody
Sorry, I
else?
lost my connection in between because of light issue. So the parameter in the can you go up? The parameter here is k in pi1.
Yes, pi2 the parameter is t.
But in the figure, it is pi1 t1, na? So I am confused about that.
What do you mean by pi1? It is
No, sorry, I t. This is.
this is an input for pi2.
Oh, okay. Sorry. Yes.
I mean, I prime is like anything. I mean, it doesn't matter, right?
And we are aiming fk. So we are aiming an algorithm for pi2 that is parameterized in k, right?
What is k for pi2?
Okay, there is nothing like k. So we are aiming an algorithm for pi2 parameterized in t. So we need to restrict it to t. Yeah. Otherwise,
How many of you are really confused? If you are really confused, can you put +1?
I think it should be a function of t only.
Okay. Okay, tell me honestly, why did you say that it should take polynomial time here? Hello? Did you have any reason to say this should take transforming an instance of B to an instance of A should take
Because the
polynomial?
reduction time plus the running time of A should be less than equal to some polynomial time.
Great. So let's write down this, no? Okay. So as you say, reduction time and what, Sona?
Running
Transformation.
type of algorithm A.
And running time of A should be equal to poly in N, right? Is that fine? Okay. Now let's import the same idea, no? What's the problem in life? Now I want, suppose, like that this should be some function of what?
T.
Some say some function of
T.
T.
okay.
Yes.
So what should the reduction time be bounded by?
Some function of T.
Function of T and running time of A?
Same.
Are you sure, Sana?
No, running time is function of T
Okay.
multiplied by the I power constant.
Yeah. I'm not talking. Let's not worry about the polynomial function.
But it should be a function of k, no? Because
Why it should be function of K, Nidhi?
it's given that problem pi1 can be solved in
Solved in
FPT in FK.
K. Okay, very good. So here are two things, right? I have an instance I comma T. I transformed into an instance I prime T prime, and all of you have agreed to this, that this should definitely take time, some H1T times some instance to the power big O of 1, and I have produced this, right? Now on this, you are going to apply your algorithm A, which is going to take time. How much? How much it will take? If I give him this instance I prime T prime, how much time it will take?
F of T prime.
Is that correct, Nidhi?
Yes, if I prime T prime is an instance of pi 1. Yeah, now because of K is equal to T prime.
K, oh, there's nothing called K. It takes a parameter. K is a number. Okay, this is what it took. Now, I want all this to be, so what I want, H1T times big O of order 1 plus F of T prime times I prime of big O of 1. I want this to be less than equal to some
F of T or some other function.
Function of T.
something. This is what I want. And this I is this I that I started with. Okay, two questions. Question number 1, what T can be? What T prime can be?
T prime must be a function of T.
And what I prime can be?
I prime will be polynomial in N. I prime will be polynomial in I, and T prime will be some function of T.
How many of you agree with her assertion?
I prime can be also some FPT, some F of T, G of T also.
Okay, so what he says, what about if I prime, for example, why can't I prime be say 2 power T times I? What will happen this? What's wrong in it? All of you say that T prime be better be some function of T alone. But there is no reason to assume that I prime has to be some, like I prime could also be, what do you call it? Some function of T, comma, this polynomial in this. It could be as big as this. Is that fine?
Yes.
Right. So this is all that I'm trying to tell you, that like you just have to go, I mean, check. Basically, there are very simple things, guys. What algorithm I'm trying to design, that algorithm puts certain constraint on the allowed running time on this. So what we know now is that in our reduction from say, in our reduction, right? Like new parameter should be function of old parameter. Okay, that's one thing. And secondly, allowed running time is FPT. Okay, so these are the two salient features. Okay, now I'm going to ask you a following simple reduction. Okay, so all the class we have talked about only one problem. Okay, vertex covered. Okay, and let's talk about its cousin brother independent set. What is the reduction from in vertex covered to independent set in classical setting?
Take the complement. Right? If we take G to G, same graph, and if G has a vertex cover of size K, then G prime will have a independent set of size N minus K.
At least. Okay, so what's he saying? That look at G comma K. Okay. Okay, so let someone else let me tell. Okay, so how much time does this reduction takes? Time?
G has an independent set of size at least n.
No, sorry, you're right. Okay, so what is the running time of this reduction? Polynomial, right? Is it a FPT reduction?
No,
Why?
because here the n minus k, it's not bounded by only k. It also contains n in it.
So the point you have to notice that in this reduction, k bends to n minus t. Now the parameter is k here. Okay. Now, if you wanted to give a reduction, parameterized reduction, it is important that the new parameter, which is n minus t, right? What should be this? It should be also a function of k. But in general, n and k have absolutely no relation, right? So we cannot say that this is always going to be bounded by some function of k. So this is one reason why not all polytime reduction, many one reductions are also parameterized reduction. So parameterized reduction, it is very important that the parameter that which you are transforming into is controlled by a function of the parameter itself, but I allow you much more running time. So I do have some leverage that I can take much more running time to construct such instances, but I also have a constraint that k cannot grow too much. Okay, so this is why this simple reduction does not work in terms of what is that called? What do you call in terms of FPT reduction? But there's another simple reduction that you must have seen in your algorithm course is, let's say, click problem. Input is G, K, parameter is K, and the question is that G has a click of size at least K. Can you come with a reduction from independent set to click? The classical one.
Independent set instance G and K,
Okay.
and take the complement of the graph and instance same, parameter same.
Okay. So G has independent set of size at least K if and only if G bar has click of size at least K. Okay. What is the running time of this reduction? What does K goes to?
K.
So is this an FPT reduction?
Yes.
Okay. So if I knew that click does not have any f of k n to the power 1 time algorithm. Suppose this is my assumption. Okay, the way I assume 3 SAT or SAT does not have polytime algorithm, this is my assumption. What does this imply immediately? What did we deduce from? Just now we deduced.
Independent set.
Independent set doesn't have.
Okay, so we are going to make a complexity around click. Okay, so this will be our working assumption. Okay, what is our axiom? Just remember, axiom is this. Okay, click does not have f of k n to the power big 1 time algorithm. Okay, that's it. This is our axiom. Okay, given this axiom, what is the first theorem just now you proved? Okay. And let's call this axiom, let's give them same, call it clique hypothesis or whatever you want to call it. Clique hypothesis. Okay. So we just now prove unless clique hypothesis fails, okay, independent set is not FPT or does not have f of k n to the power big 1 time. So problems in parameterized complexity that do not admit such algorithms are called W1 hard. Okay, and we are going to build the theory around clique hypothesis. Okay, and this is all that we will do. Okay. Okay. So now I'm going to go back. There were lots of problems. Okay. What is the best known algorithm for all pair shortest path? We'll come back to this word, but I want to build something else before I come back to this word. You know what is the best algorithm for all pair shortest path?
In between n cube, like n cube divided by some logs.
Yeah, so like, okay, say roughly log order n cube, right? So for how many years we have not seen progress on APSP? For a long time, right? Okay. So what is the natural question to ask? Is n cube the real barrier, or does there exist n to the power 3 like algorithm? Like this is what you, if you look at the website, called purely subcubic algorithm, right? Or you will hear purely subquadratic algorithm. You get my point? So for example, single source shortest path, it has a quadratic time algorithm, or for diameter finding, radius finding, and this, that, all those kind of things. Okay. Diameter, we can do it in order n square time, right? Now, a lot of questions people have asked themselves that what can we say about all these kind of problems? So one way could be, so for example, one way could be that, okay, look, if we could make a world around APSP, right? We say, okay, look at this bunch of problems are there. If for any of them, you can get sub-cubic algorithm, right? Implies APSP has cubic algorithm, right? Then again, suppose one has such an algorithm, right? Then for using that algorithm, you will create an instance of APSP. And now you tell me how much should we allow such reduction to take? Given an instance of APSP, I want to produce an instance of some problem A. How much should I be allowed? If I want to rule out, if I want to design n to the power 2 minus epsilon algorithm.
N power 2 minus epsilon.
Huh?
N power 2 minus epsilon.
Yeah. So then, because we are trying to rule out only n to the power 3 minus epsilon algorithm, then I can only allow the reduction to take n to the power 3 minus epsilon. Plus, now instance shouldn't blow up. Instance cannot blow up if I'm going to assume that A takes time n to the power 2.999, then the size of instance had say n, now n prime, that the new size, you should have that this is less than equal to n to the power 3 minus epsilon prime. You get my point, right? So this is how you design such an algorithm, such kind of complexity class. So you can pick up your favorite problem and you can make a complexity around them. You can define a reduction, define the completeness, whatever you feel like. Okay, but you have to appropriately define what the reduction means, how much running time is allowed, and that is very easy. Like you just see what is an output running time you want to avoid, and you allow lesser than that or at most that much amount of time to do every action. Okay. Okay, so now imagine, okay, so that much I have told you. Okay, so before I go to the click hypothesis, in the world there are just 3 hypotheses basically, and like more or less. One is that SAT, 3SAT can't be solved in P time. Okay, so this is but like this basically means unless P equal to NP, something happens. But then after 30-40 years of hard work for 3SAT, we were not able to design an algorithm which is running time 2 to the power little of n, where n is number of variables. But do you know any algorithm which is like any algorithm for 3SAT in terms of variables?
To the power n.
What will you do to 2 to the power n?
Like all possible assignments.
Okay,
Oh,
brute force. Okay, so here's an exercise, guys. Or rather, let's say this is an assignment. Design 2 minus epsilon to the power n time algorithm for 3SAT. Okay, so that's an assignment. Okay, but now when I say 2 power little of n, what do we mean by 2 power little of n? 2 power little of n, can we have an algorithm with running time, say n log n divided by log n, or n even smaller, log star n, or any f of n, where f of n is monotonically increasing function. Like any monotonically increasing function can be designed such an algorithm. Okay, we are not able to do it. So when people are not able to do it for a long time, this in some sense starts to convert that, okay, is there something interesting happening because of this? So they came up with what is now known as exponential time hypothesis. Guys, this is just an overview. Don't take it like there's just some precise definitions to it, but this is 99% enough for you to do most of the computer science. Okay, so what is the exponential time hypothesis, or ETH, is the following. Okay, ETH. What is exponential time hypothesis? So it basically says 3SAT can't be solved in 2 to the power little of n time. That's it. So now, once this is an assumption, you will see a lot of theorem people prove unless ETH fails, blah, 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 blah. Okay. Okay. But now so this is our okay. So this is our first assumption of the world. Okay. This is our second assumption of the world. Okay. And there's a third one, okay, which is very powerful. And the third one is like, look at SAT. Okay. No restriction on formula, clause length. Okay. For this also we have 2 power n algorithm, right? What all of you said, brute force. And let's ask ourselves another assignment. Designed 2 minus epsilon time n algorithm for SAT. Okay. And till you solve your assignment, we will make it an assumption. So what is an assumption? Is that SAT does not admit an algorithm with running time 2 minus epsilon to the power n for any epsilon. Okay. And this is what is called set, or what's it called, strongly exponential time hypothesis. Is that fine? And I also told you about clique hypothesis, right? Which is a backbone for FPT versus W1. But actually, we could build our theory directly from ETH. Okay, they are uncomparable, but directly from ETH, we could build our theory. Okay, in the sense that we'll say, look, if clique is FPT, implies 3 SAT has 2 to the power little of n time algorithm. Okay, so we could start proving such things, reductions, but I will come to that a little bit, like these kind of things. I will come to that, I think, in a week later, a week later. But for now, what I'm going to do is going to start from clique hypothesis and show you some interesting reductions. Okay, any questions so far? Anybody? Okay, or let me ask you a question. Assuming set strong exponential time hypothesis, can you come up with some lower bound on set cover? You know what set cover problem is? Let me have some fun today. Okay, what is set cover? You have universe, family of sets. And there's nothing about parameter. The question is, does there exist a family F prime subset of F of size at most K such that union of F in F prime is equal to polynomials. Okay. This is set cover. Okay. So what does set tells us? Set tells us that SAT can't be solved in time 2 power n, where n is number of variables. Starting from this, can I come up with a like a concrete lower bound on set cover?
We can reduce set to set cover, and we can use the reduction time to get a lower bound.
Okay, so what can you rule out? Okay, so let's ask ourselves, can set cover has say 2 to the power mod u by 4 algorithm? Let's rule out this if possible. Can we rule out this algorithm? So set cover has no this time algorithm. Okay, can we rule out this? If I wanted to rule out such an algorithm, what I need to show, what I need to do?
But if this
Suppose
can be
it has
done, then
What? One by one, please.
okay, so we can rule it out by assuming that assuming set cover has this algorithm and showing a reduction from SAT to set cover, then it will
Mhm.
contradict that SAT also has this algorithm. It will contradict set.
Okay, so what's he saying? That let's start with SAT, give a reduction to set cover, and use good algorithm for set cover, okay, to design good algorithm for SAT. Am I right? Okay, so for set cover, what it takes, so set cover we have, and suppose we have an algorithm for set cover which runs in time, say 2 to the power big U divided by 4. Suppose, so let's suppose we have such an algorithm. Assuming this algorithm, can you design 2 minus epsilon to the power n algorithm for SAT? That's my question, right? Using a 2 to the power big U by 4 algorithm for set cover, can be designed faster than 2 power n algorithm for satisfiability? Anybody? Okay. So what does instance of SAT cover, like what does the fee consist of? C1 or C2 or C3 or CM, M clauses. How do we transform this into universe? Into a set cover instance.
Each clause is a set.
Take every variable, each yeah, go ahead, Shriram, sorry.
What is my universe? Some new person should tell you. Come on, what is my universe in this case? And what is my family of sets? Okay, Siram, you tell. People are not happy to tell.
Take universe as the variables and
Okay, so
F as
suppose
the
my variables are say x1, x2, xn, right? So universe, you are going to take x1, x2, xn. Am I right?
yes,
Okay, what's my family?
clauses.
I think there is a clauses. So suppose I have xi, x1, or x2 bar, or x3. What should I take? What should be the corresponding clause family? Suppose this is my clause C1. What should be the family for this, or the set for this?
We'll take negations also in the universe.
Then you have
X.
to take universe literals, not just.
Okay. And now clauses. What should be in the F1? So what's my set corresponding to my clause?
X1, X2 bar, and
X1, X2 bar, X3.
Okay. So corresponding to each clause, I make a set, which is basically you just take the sets containing the so given Ci, make Fi a set containing literals in Ci. Is that fine? Okay. So is this enough? Okay. And what is the role of K here? What is K here?
we must have K sets that will cover the universe.
So what is that K?
K is the how many variables should be true in the assignment for SAT.
Yeah, but we're just talking about normal SAT. There is no assignment. So what should we do here? There's something wrong, no? Okay. Maybe you didn't like the problem. Okay, so okay. Do you see the difficulty here?
Looks like hitting set.
What? Okay. So people are saying that, okay, set cover is not the right thing to do. So, okay, let's say they all are talking about something called hitting set. So what is hitting set? Okay, so fine. Let me write down hitting set. Okay, so what is hitting set? So hitting set is that input is again universe and family. Parameter is K. And the question is, does there exist X subset of U mod X equal to K at most K, and X intersects every set in F. Okay, so this is what it is. Now, the reduction which you people have been talking about before, that you started with a SAT, okay, and you did universe equal to x1, x2, x1 bar, x2 bar, dot 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 xn bar, and the family F had F1 up to Fm, and what is Fi is basically literals in clause Ci. Okay, now what should I do? Is this like, how do I, what is K again? Come on. Like, is this reduction complete? Think about it, no? Yes, Prateek?
If there's a hitting set with x1 and x1 bar, then
Yes.
this maybe the satisfying couldn't be able to.
Correct. So what
we
should
might
we
not
do
be
then?
able to find a satisfying.
So what should we do,
Like the
Prateek,
if
to
and only
avoid
if in the
that?
other direction.
So Prateek, what should we do to avoid that? Can we do this? Add following kind of sets. Right. And I substitute K equal to N. Does that make sense? Now notice, because your budget is just N, right? And these are disjoint
Sorry,
sets, right?
Saket, I don't understand why have you introduced these sets. Could you please repeat?
What?
Why have you introduced this x1, x1 bar, these sets in F?
Because what he says that, look, if I'm giving a reduction from SAT and your set cover consists of x1 and x1 bar both, what meaningful sentence that can I derive from there? If you picked up both, look at the reverse direction of the reduction. If the set of vertices which intersect every set contains both x1 and x1 bar, what can I set for SAT? There's no consistency between x1 and x1 bar. Okay, so to bring down consistency, I did this A, and then I introduced K equal to N. Why? I said, look, you can only pick N size set, which implies, look at x1, x1 bar, look at x2, x2 bar. These are pair by disjoint sets. How many of them are there? N of them are there. Now, if I'm looking for N, so any hitting set must pick up one vertex from each of this double clause. It has no choice. But it picks up, so now I'm sure that from x1 and x1 bar, I have picked up just one of them. From x2, x2 bar, I have picked up only one of them. From xn, xn bar, I have picked up only one of them. Now, notice that I have a proper bijective correspondence between set I pick and the assignment. Is that fine? I have not showed anything. I have not proved anything. It's just my construction. Now, what I want to say that what is our lemma? SAT, like phi is satisfiable if and only if U, F, comma N is yes instance. Okay, why? Now look at, if phi is satisfiable, it means I have an assignment. If phi is satisfiable, means there is an assignment that x1 is assigned 0, x2 is assigned 1, xn is assigned something. Okay, in this case, what happens? What will I go and take? I will take x1 bar, right? Because x1 is 0 means x1 bar is set to 1, right? x2, xn, and whatever. So this is a subset f of u. What is its size? It is exactly equal to n. And I claim that it hits every set. Definitely it hits every two side sets. Now look at any clause, right? My formula was satisfiable. It means one of the literal was set to 1, right? And if that is set to 1, then what I've taken from each of the guys which are associated here, I have taken that one of them, must have taken into, because of the assignment, I must have taken in the set S. It implies that that particular set will be hit. Is that fine in the forward direction? Right? What's the forward direction? Look at any set F. Okay, I have to show that it intersects all this. One of the, suppose it does, and if you know that this is a satisfying assignment. If it is a satisfying assignment, it means some literal is set to 1, right? So if, and what I have done, all the literals that are set to 1 is what constitutes our set S. That implies that this literal is also part of the set S that we have constructed. Is that fine? Is that okay with you, all of you people? Okay. Only 2 people understood, Sonak and Sally. No. 4. So Pratik, now does it takes care of your what do you call issue? Okay. Another thing that I wanted to tell you, since you brought this up, Pratik, is the following. Okay, whenever you make reduction, no, in most times we have some, like there will be a piece of gadget where there is a, in some sense, 1-to-1 correspondence between feasible solution in the left hand side and potential solution in the right hand side. So here, what are feasible solutions in set are all possible assignments. And what will those possible assignments will correspond to is like doing some selection across these sets. So like these are like forming a selection gadget. So looking at this selection gadget, I can constitute or construct an assignment for my left hand side object. So this, like when we are trying to construct the gadgets, this is something which is always behind our head. Okay, now let's look at the reverse direction. Reverse direction, we need to select a set S subset of U mod F is less than or equal to. Now, because we introduce x1 bar, and any hitting set must intersect this, it means from each of them we would have picked up x1, or we have picked up something, we have picked up something. Now go assign these literals, right, to 1. If you assign these literals to 1, you are done, because now you look at any clause that corresponds to some this thing. From this, you must have picked up one of these literals and you are done, right? So this is a very simple if and only if reduction that is happening in this case. Okay, is the reduction clear to everybody?
No.
Yes, Pratik, tell me. Yes, Pratik.
It could. Oh, okay. Yeah.
Look, Pratik,
So
look at the
S
reverse direction.
at most
Yes.
N. Okay, yeah.
Yes, that is where the number comes into play, Pratik.
So that is where. Okay.
Yes, that is why we needed to have at most k. So this is why by setting k equal to n, we are, so this is another way in gadget, in like, so one thing, like you use weights to control things, you use numerics to control things. So I have used k to control things. So I'm not looking for any solution of size, like any solution, but I'm looking for hitting set of size at most n that forces us to pick exactly one from each, and that exactly tells us what assignment does it correspond to. Is that fine?
Yes, now it's clear. It's not an FPT.
No. There's
right.
nothing about FPT, Pratik. Absolutely nothing about FPT. Okay. But I want to, let's see how good things that it rules out. Okay. I just want you to show something. Okay. It has nothing to, it's not an FPT reduction. Okay. But now notice I started with a field. How many clauses and variables it has? N variables and M clauses. Now I have universe and family and some k. What is the size of my universe and size of family? What did you take in your universe in this reduction?
Universe is 2n.
The number of.
Right? And m plus n. Okay. And what did we assume? We assume that hitting set does not have 2 to the power mod u. So suppose this, and you know that this algorithm takes 2 to the power u by 4. Okay, there is an algorithm. Okay, what we know, suppose this is our existence algorithm. Okay, there is an algorithm for hitting set running in time 2 to the power mod u by 4, suppose, and n plus m to the power big O of 1, right? What does this imply because of this reduction? That you can design an algorithm for SAT in running time. How much? This implies SAT can be solved in time. How much? Can please someone tell me? I have written all the things are here. From looking at this, please tell me how much time, with the help of this new hitting set algorithm and the reduction that we built, we can design an algorithm for SAT. So how much time do you take to transform phi to this instance? You tell me, how much time did you take? Huh?
Polytime.
Polytime. Excellent. And now you're going to run this algorithm. How much time will that algorithm run?
Raised to power 2n by 4.
Right?
N plus n.
Okay. But now, given an answer to this, how much time will you take to get an answer for SAT? If I gave you an answer for set cover, how much time will you take to get an answer for SAT?
Polytime.
Oh, I shouldn't be writing n plus, I should write n plus m. Okay. So what is the total running time of this algorithm?
2 to the power 2n.
Does it contradict Seth?
Yes.
So what can we, in fact, we could have assumed something like we can rule out that not only this, in fact, why y by 4? Or like I think we can push this up to y by 2, no? Because if you had slightly faster than u by 2, then you will get better than 2 power n algorithm. Do you understand? Did you get this point? No.
If we put 2, then it will be 2 raised to power n. only, no?
Yeah. So that's what it says. Slightly.
So,
So
we
for
need to take
example,
something
so
slightly.
suppose you can say,
Yeah.
you can rule out no algorithm for hitting set running in this kind of time. Okay. So now all I want to tell you that, look, just because the parameter of our interest blew up, right? The kind of lower bounds we are able to prove on this problem also blows up, like changes, right? Okay. How many of you know diameter problem? Do you know diameter problem? Okay. Diameter is maximum of shortest path between pair of vertices. Okay. Do you understand what I'm saying? Right. So for every pair of vertices, you find the shortest path, and then you what do you call? Then you take the maximum of this. And this can be done in, if you're given an n vertex graph, you can do it in big O of n squared time. Okay. 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 Here's a exercise. Okay. And please, guys, like when I say this, guys, this kind of exercise, please think about it. Okay. Don't look at Google or something. Okay. Like this is really an exercise. Last one of the teacher. This is an exercise. Show that if diameter can be solved in time, say n to the power 1.5, okay, then SAT can be solved in time 2 minus epsilon to the power n. Is this clear? That if diameter you can solve in say n to the power 1.5, then SAT you can solve in 2 minus epsilon to the power n. Okay, so think about it. Next time I will give you this reduction anyway. Okay, but I still okay, but do think about this reduction. Okay, so all I've been trying to do is this. Okay, now can someone tell me a reduction from 3 SAT to vertex cover? Do you remember a reduction from 3 SAT to vertex cover? A classical reduction. Anybody?
Yes, sir.
So tell me.
For every literal make a vertex.
For every literal make a vertex. So this is like x1 bar, like this.
Yes, sir. For every possible literal make a vertex.
Okay, I made.
And within a clause, connect all the vertices in a clause.
Okay, so basically what you are saying to me is that, okay, so make a click on the clause.
Yes, sir.
Okay, so suppose x1, x3 bar and x5 is there, then it is like triangle like this.
Yes.
Is that correct?
And connect xi and xi bar.
And connect xi and xi. Okay.
Yes.
Should I clean this reduction a little bit just for our own?
Okay.
Okay. Okay. So just to spread this out. Maybe should I spread this out? No, this is fine. Okay. This is a useful reduction. Okay. So let's keep this reduction. Let me tell you my reduction. Okay, which is a bad one. It has its own advantage. We'll come to that in a near future. So here's another reduction from 3 SAT to vertex cover. Okay, I'm just going to open it up this. Okay, and there is reason for it. So my reduction is going to have a matching. How much? Inside matching. And they're going to be like, they're just going to represent x1 bar, x2 bar, xn bar. Okay. Now, notice that a vertex cover of size at most n corresponds to what? In this, it corresponds to selection of an assignment. So a satisfying an assignment of 3 SAT and selection of vertices in my vertex cover are in correspondence to each other. So this is what I call my selection gadget. So I draw them. Okay. And I have a relation. A vertex cover of size at most n corresponds to a what? Corresponds to assignment. Okay. And assignment corresponds to a vertex cover in this little graph where everyone is matching. And because they are matching, you have to pick at least one in any vertex cover. Okay. So that's like a bijective correspondence. Now for every clause, I want to add constraints. So suppose you have clause A bar, B, C. Okay. Now what I will do that I will go and add A bar to A, B to B, and C to C. This is how I will hang this. Okay. Now notice that in this also we can show that I'm looking for a vertex cover of size. So every triangle, I must pick 2 vertices in the vertex cover, right? And from every matching, I must pick 1. So I will say the vertex cover of size at most n plus 2m, right? Okay. You can show that phi is satisfiable if and only if g phi comma n plus 2m is a yes instance of vertex cover. This is also not my reduction. This reduction is there in CLRS or any textbook. Okay. And this is one reduction which Yash or Gaurav told. Yash?
Yeah, it was.
Okay. Now, but there are some very fundamental things which are different in both reduction. Okay. So the first reduction, look at the first reduction. We had phi, we constructed g phi, and how many variables were there? N variables and m clauses, where m, and how many variables were there here? How many vertices were there in this graph?
2n.
2n, excellent. And how many clauses were there here? Or how many edges are there? At most 2n choose 2. Am I right? But what was the parameter here? What is the vertex cover size you are looking for? N or 2n? This is your reduction, right? So what is my vertex cover size that you are talking about? Or this is like some optimization version? What is this? Do you understand?
We are looking
question?
for.
Yes.
Yes, sir. Yes, sir. We're looking for n size vertex cover because only then we'll get enough.
Okay. So what's he saying? What he is saying that you are looking for an n size vertex cover. Why is the forward direction okay? Let's see. Why is forward direction okay? Why any edge is covered? Does it not sound something fishy? What did you do? You took 2n variable. For every clause, you picked up those 3 literals and you made into a clique, which is like a triangle. Am I right? Now,
Yes, sir.
Now what you are saying to me is that look at phi is satisfiable if and only if, phi is satisfiable if and only if you have a vertex cover of size at most n, right? Now look at the forward direction. So from x and x1 bar, x and xn bar, we'll pick only one vertex. Now, why it is true that for every edge, there is a vertex which is in the vertex cover? Is that clear to you? Anybody?
I think if you make a click on the clauses, then it is okay. Not
So
x1, x1 bar.
Then?
For every clause, make a click and then add the edges he added. Then 3m is the number of vertices and 2m is the vertex cover.
Then this is exactly the reduction which I did, no?
No, but your size is how much? 3m plus 2n, right?
N plus 3m.
No, but yes, but 2n plus.
Oh, right, 2n plus 3m.
But in mine it is 3m.
What do you mean by mine is 3m?
Means if you take every clause,
okay,
then the 3m vertices, right?
Each clause contains 3 variables and there are m clauses. So how many variables, how many vertices did you have?
3m.
3m. And
Yes.
how many this x1 bar, x2 bar, how many of them are there?
No, there is no other x1 bar.
Okay, you're just saying, okay, fine. Okay, you make a click on x1 wherever they appear.
Yes.
That doesn't
Then-
matter. Okay, so this reduction was at least buggy, at least it didn't go through. Okay, then let's stick with my reduction. This is much more cleaner. Okay. Okay. But now notice that I have 2n plus 3m vertices, okay, in this graph. Now, all I know, suppose I knew that you cannot have 2 to the power little o of n algorithm for 3 set. What can I rule out about vertex cover with this reduction? Or with whatever he made a reduction, which is, I say, maybe slightly better, say 3m. What can you rule out?
3m reduction won't work. Backward direction, there is a problem.
Okay, ठीक है भाई. Okay, okay guys. Let's just stick with it. Okay, yeah, you can discuss this later. Okay, offline guys, offline. Okay, okay, because we will lose what we want to learn. Okay, so 2n plus 3m we have. So what can I say about 2 to the power little o an algorithm for 3 set? We know doesn't exist. Using this assumption, what can I say about vertex cover? So we have 2n plus 3m. How much can it be? How much m could be? How much m can be? How many clauses are n variable? How many clauses can an n variable 3 set formula contain?
Two n choose 3.
Yeah, which is like order n cube. Okay, fine. So what can you rule out for vertex cover? Can vertex cover have an algorithm with running time where n is number of vertices in graph? Can this possible? Please tell me. Unless ETH fails, what can you say?
There is a 2 power and 3 by 4 algorithm.
So then what I can do, I can apply my polytime reduction into the power big of 1, apply this algorithm, which will, so, but now my instance is like, could be n cube, right? So it is n cube to the power 1/4, right? And getting this solution. So this is an algorithm which runs in time 2 to the power big O of n 3/4. Is it 2 to the power n to the power 4? Is this 2 power little o of n? Yes or no?
Yes.
How many of you agree that 2 to the power n to the power 3/4 is a little of n?
Yes, it is.
Okay. But like, so how far can we go? With this reduction, how far can we go? Roughly 1/3 minus epsilon. We could rule out, right? No, this time algorithm unless ETH fails. Is that fine?
4 minus epsilon, right?
No, I say 1/3 minus epsilon. Because look, in this, otherwise what will happen? 2 to the power big O of n cube 1/3 minus epsilon. Right? Please show that this is 2 power little of n. Is that okay?
Okay.
I mean, you just choose different epsilon, right? Okay. Okay. So something you can get, okay? But we don't know, right? But what we can actually, we will be able to rule out sooner or later that vertex cover does not have unless ETH fails. Okay. So what I have done to you, that I have shown you that if you make different assumption on this algorithmic running time of satisfiability, you can start proving different kind of reduction. If you assume polytime, then you can rule out certain polytime of algorithm. If you assume 2 power n, then for a lot of problem, you can start to rule out certain very bad exponential time algorithm. If you're going to assume some asymptotically little of n, then you can start ruling out something else. So every NP hardness, if you look trace back, it will rule out something. But what is a ball of the game is, can we come up with something asymptotically tight, right? We say, hey, this is possible, and asymptotically you cannot do better than this. Okay, and that is a fight we play using these stronger assumptions like ETH or strong exponential time hypothesis, or people define whatever they call orthogonal vector or 3-sum or 4-sum. I don't know what all things are there, but like you name it. Okay, so we will spend a few weeks playing around with this, storing some W1 hardness or hardness in parameterized setting, and like tight hardness, like f of k is tight, like 2 power k to the power 3 by 4 is possible, but k to the power 3 by 4 minus epsilon is not possible. Things of this nature. Okay, so till then, I'm done.